So far, what we've discussed in terms of expert systems are straightforward things, right? By straightforward, I mean things that are very clear cut, this or that, yes or no. Remember those statements also we mentioned, true statements, false statements. Now, this is an extension to what we have discussed, and that's why we call it fuzzy. Now, what do we mean by that? You might have heard people or experts use, they rely on common sense knowledge to solve various problems. So we say that this type of knowledge is exposed when you might hear an expert saying, when the motor is really running hot, I decrease the speed a little, right? So, and we're used to hearing this description quite often, every day. And as humans, since we're so used to it from day one, that we have little difficulty in interpreting the use of these vague terms, right? Now, the challenge is, how do we provide the computers with the same level of understanding as we have built, as we have developed? And that is a challenge. And that challenge, the answer to that challenge is, in order to represent some things which are vague, ambiguous, or into a computer system, we use fuzzy systems or fuzzy logic. Fuzzy logic is primarily concerned with quantifying and reasoning about vague or fuzzy terms that naturally appear in our natural languages we use every day, as I said. Okay. Now, in fuzzy logic, these fuzzy terms are typically called linguistic variables. Linguistic variables. Linguistic relates to language, and also called fuzzy variables. Okay. So, what are typical linguistic variables that we come across? For instance, you say a linguistic variable, a temperature, for instance. A temperature can have, let's say, two values, hot and cold, for instance. Height, for instance. Height, you can say another linguistic variable used in language, and it can have values like short, medium, tall. Speed of a car or bike or whatever, that's a linguistic variable. It can have values like slow, creeping, crawling, and fast. Now, each of these, okay, in each of these, there's no specific value associated to it. There's a fuzziness, a concept behind the mind, and we try and interpret. And that's where, in fact, people have different opinions as well. How cold is cold? When you feel cold, do others feel cold as well? Right? However, we still use it, and we do it every day, every time, all the time. Okay. So these linguistic variables, they are used in fuzzy rules. Now we're moving from typical expert systems that we've discussed to fuzzy expert systems. Okay. And so we use these linguistic variables in the fuzzy rules that we talk about. So in general, we are living in a vague world, and we humans like to talk in terms of things like maybe, perhaps, probably, okay, feels like. So each of these are fuzzy values, fuzzy things, fuzzy concepts, and they cannot be defined with 100% authority, okay, when we use these terms. As I said, you might feel cold, others may not. You might feel hot, others may not, and so forth. Conventional computer programs, they cannot understand natural language. Okay, they're not designed to handle vague concepts. So statements such as Umar is tall are difficult for computers to translate into definitive rules. On the other hand, let's say you say Umar's height is 162 centimeters. Of course, this is precise, but doesn't explicitly tell you whether you consider him short or tall. Now, this brings me to a very basic discussion we have been talking about. We have talked about sets of things, okay, typically called classical sets. Well, they've been around for a while. So you have a set of glasses, you have a set of integers, for instance, very common, right? Now, when you say this is a set of integers, anything which is not integer is not part of that group, okay? So they are very crisp values, very sharp values, clear cut values. So we have a crisp set of things. And as I said, you have very clear cut boundaries. Either something is part of that group or not. There's nothing in between. There's nothing in between. Either completely part of this or not. A set of, as I said, integers. If it's an integer, it's part of that group. It's not an integer, it's 1.2, for instance, 1.07, 35.235 is not part of the integers. So yes or no, right or wrong. That in fact also is the binary system working, only two valued. Okay, so crisp sets, okay, are for very clear cut things. For example, the days of the week. Okay, you have 7 days to the week. A crisp set will include all the 7 days, okay, Monday through Sunday, as part of this set, okay, crisp. And everything possible other than this, anything, like doors, cars, monkeys, computers, fish, anything else is not part of this set. It's very, very clear, crisp. Now the boundary, there's a binary classification, of course, and the boundary is the real thing. You cross the boundary, you're out. You're in there as long as you're within the boundary. Fuzzy sets, on the other hand, unlike crisp sets, they don't restrict themselves to something lying completely in one set. And if it's completely in one set, it's completely out of the other. That's the crispy thing, right? A fuzzy is not like that. They allow things to sit on the fence, on the boundary, that are closer to the human world. So let's say the weekend, for example, days of the weekend. Now, the crisp set would strictly say that only Sundays and Saturdays are part of the weekend. That's correct. However, most of us human beings would also agree that we do tend to feel like it's a weekend somewhat on a Friday. So if we were to represent days of the weekend, crisp set would say, all right, Friday is out, Saturday, Sunday is in there. Okay. If we were talking about fuzzy sets, then we would like to place the Friday on the boundary, the edge. So as I said, since you feel like Friday being closer to a weekend, so mentally you think you're just about at the start of the weekend. And Sunday, for instance, you may not feel towards the close of Sunday that's part of the weekend, because very soon it's going to be Monday. Remember the term Monday morning blues, right? So people coming out of their weekends onto Monday. So this has been represented in the graph again. And as you can see, Friday somewhat falls in the days of the weekend, okay, in a crispy world. Another way of showing that, and you can see Saturday, Sunday very clearly, yes, weekends, and Friday out, Monday out. Whereas in the thing that I just referred to, you can see that these are not clear-cut boundaries, the kind of sloping things as you've seen. So from two-valued thing, you're moving to multi-valued thing, right? That's the idea. Application. Now, fuzzy systems has been around for quite a while. And typical applications are self-focusing cameras, washing machines that adjust themselves according to the dirtiness of the clothes or the weight of the clothes as well. It might add more water, it might reduce water, it might increase the wash cycle or the dry cycle, and so forth. Perhaps anti-lock braking systems, subway control systems, computer programs trading successfully in financial markets. So now coming back to how do we define membership or membership function, because something belongs to this group and also belongs to another group. That we in this world that we're talking about. Okay. So this is the degree of truth that we talk about. Okay. And that is determined by something we refer to as a membership function. A membership function can be anything ranging from a simple linear straight line to a complicated function or some other polynomial of a higher degree. Characteristics of membership functions are that it is represented by the Greek symbol mu, and the truth values range from 0 to 1, anything in between. Now, what do I mean by truth values? Truth values, a value of 0.0 normally means absolutely not. You're not part of my group. No membership at all. Okay. And whereas in CRISP systems, you wouldn't have such a thing. You would include it or exclude it. But here you say the membership value is 0.0, you will still say that and say it's a 0 value. And a 1.0 value of the membership function, that would represent absolute truth, full and complete membership, right? So the essential thing I'm highlighting is partial membership to a full and complete. The partial membership of this group as well as the other group. Okay, so you're either part of this and part of that, both, and that's represented by the function I just mentioned. Let's consider another example. Ammaji is old. She's an old person. In CRISP set terminology, Ammaji would be part of the old people. Okay, and here we defined mu, the membership function mu old, as the membership function that operates on the fuzzy set of old people. It takes as input one variable, which is age, and returns a value between 0.0 and 1.0, anything in between as well. So if the age is 75 years, then our mu old membership function, given this value of 75, might return a value of 0.75. That's a membership number. Okay, don't confuse the 75 to the 0.75. We could have it instead of 0.75, just an example, 0.81 or 0.82 or 0.74. So don't correlate the number to the membership function. So if the age is 75, the membership function mu old, given this age, would return a membership value, which in this case I'm taking as 0.75. This would really mean that she is quite old. Ammanji is old. In another case, if we give that membership function an age of, say, 20, the membership function might return a value of 0.2. So if Amber is 20 years old, and we pass on the age of 20 to this membership function, it might return with a value of 0.2. So of this function, of the old function, this would imply that Amber is not very old. In fact, not even old. 20 is too young to be part of the age group A, or old. There's also something about fuzzy and probability. I don't want to discuss, people talk about it. Fuzzy means quite clear-cut. Probability means the likelihood. Don't confuse yourself if it comes to this. Simply you concentrate on fuzzy and the values there. For instance, in the case of Amber, if the value is 0.2, probability would say that Amber, there's a possibility, that 20% probability that she's member of the old group, 20%. Fuzzy says, with the quality of being clear-cut, that she is 0.2, her membership is of the old group. So there's no chance in that. A number is not old, she is actually only 0.2. However, if you talk about another group of young people, she would have a membership of, let's say, 0.8, because she is in that age range. So no chances involved, no guesswork. Then a little bit about fuzzy and logical operators. You're already familiar with logical operators and or not. Very, very simple. And then a combination of these. Now, these logical operators, they're also, we have an equivalent of these in fuzzy as well. Okay. So moving from conventional into multi-valued kind of thing. Fuzzy systems, we do need exact operators which replicate these logical operators. So if we choose, let's say, a minimum operator between two things in place of an and, we will show you just a little while that if we use an and operator between two fuzzy things, then, and if we take the minimum of the two values, okay, you would still get the same result if you were in fuzzy sets as opposed to an and in crisp sets. Okay, and similarly, when you use the or operator in crisp values, as opposed to that, if you use the maximum operator, okay, then the two are equivalent. And mu of not a is just the opposite, replaces the not that we use typically in logic. And there it is. So if you look at these fuzzy operators on the left, you have two inputs, AB 0001-1011. These are the four values that it can have. Now, if I take the minimum of A and B, and that's the third column, you notice that both are 0, so the minimum of these two is 0. You look at the next line, you have A is 0, B is 1. So what is the minimum of these two? 0. Now the third row, 1, 0. What is the minimum of these two? Is 0. And both being 1, the minimum of these two is 1. Now clearly you can notice that taking the minimum of A and B is equivalent to the AND operator, right? I'll help you the next one as well. We have the same 0001-1011. Let us take the maximum of these two inputs. So you notice a 0 in the first row, 1, 1, 1 in the following three rows. Now clearly this is equivalent to the OR operator in our typical Boolean system. And likewise the third one, and this unary operator. So if you have 0 at the input, you will get a 1 at the output. You have 1 at the input, you get a 0 at the output, which is the NOT operator. So this will give you a clear-cut idea. The AND operator means taking the minimum of the two values. The OR operator means taking the maximum of the two values, and NOT is 1 minus A will give you that. Let's take another example. In this example, we have demonstrated, okay, the relation or comparison between two valued logic. If you look at the top line, you have A and B, and they appear to have two different values, 0, 0, 0, 1, and so forth. So the top line actually tells you the two valued logic for different, the truth table that I mentioned. In the second row, you can see the effect of these, which is A and B, and that's the AND operator taking the minimum of these two. So for first three combinations, it remains 0. For the fourth combination, it becomes 1. Likewise, the OR, which is the max of these two, and then the NOT operator. Now, look at the second, which relates to multi-valued logic. Now, notice that we have used a triangular representation. So an input A doesn't always have a value of 0 or 1. It could have multiple values, as I said, multi-valued logic or multi-valued representation, okay, which is that membership function. So A is represented as a triangular notation, and so is B, right? Which means this is a typical representation of real life situations where the max value is just about at the middle of the triangle, and all of the values before that or after that, that max value, are lower than that and represented as typically a triangle. Now, given that situation, let's just look at multi-valued logic for the very first one, okay, where we have two overlapping triangles. And remember, this identifies that something can belong to two groups, two sets as well. So if you just add up, okay, you take the maximum of these two you will see the very small reduced triangle. And that triangle is a 0 to the left and 0 to the right. And that is the multi-valued logic, the AND operator in the fuzzy systems. Looking at the next one, the OR, this means the maximum of these two. So we have in the second row, you see the same two triangular functions, A and B. If I take the max of these two combined together, I come up with a slightly distorted shape of an M. So as long as something is greater than the other, that prevails. And as long as A prevails over B, you see the first half of this triangle of the OR, that dominates. In the second part, the triangle for B, that dominates. And this is why it doesn't come down below that minimum value where the cross, where A and B cross. They don't come to that. So that's the OR operator. And likewise, the third NOT operator. So the interesting thing is that the graphs for A and B are nothing more than a distribution. Now, if A were the set of short men, then the graph A shows the entire distribution of short men. That's the first triangle for A, if A were taken as a set of short men. Okay. The horizontal axis is the height, as I just before. So you have horizontal as height, and vertical axis is the membership function. So typically, for a large population of men, and we're trying to look at short men, it would be like typically called a bell curve, but we represented this as a triangular function. Most people in large populations fall in that category. Okay, you take a height of of tall men, you will see the same thing. So for larger values, okay. And likewise, the taller men would have little or zero membership in the function of short people, okay. Whereas they would have significant membership, which let's call as set B, as tall men, they would have significant membership. So that's the thing, okay. Average height is typically, represented with a triangle, or whether that might be, short people, taller people, whatever. Fewer men are exceptionally tall or exceptionally short. And that explains the slopes around the boundaries of the triangular distribution. So this is an alternate representation to the graphical that we discussed. So I hope this clarifies things. And what have we discussed so far? We have defined the fuzzy systems, the fuzzy operators equivalent to AND and OR, okay, min versus max, and the NOT operator, and how to represent these. I hope you found this useful. It's a very interesting subject, and we'll come out with more in the following videos. Thank you very much.